Welcome to homework.
Hello everyone, today we're doing chapter 14, problem 42. And this question asks us that how can we use chemical shift and integration data for these proton NMR spectros to distinguish between each pair of the following compounds? And it's telling us that the HNMR spectrum of each compound only contains singlets. So how can we use the chemical shift and integration data to distinguish between these two compounds? Well, let's determine the number of chemically unique protons between the first pair, these two right here. So obviously we have 3 protons in these terminal carbon groups, each having 3 protons, for a total of 9 protons here. Then we have another 3 protons on the other terminal carbon here. So since we have 2 unique chemically distinct protons, we can determine the ratio between them. So here we have 9 protons, here we have 3. So there's a 9 to 3 ratio, which reduces down to 3 to 1 ratio. And specifically, it's 3 blue protons for every 1 green proton. Now what about this one over here? So this one has 3 protons here and 3 protons here. So there's a 3 to 3 ratio of these chemically unique of these chemically distinct protons. So you'll get a 1 to 1 ratio. But what about the chemical shift value? So we see that these protons in green are just adjacent to a carbonyl group, while these protons in blue are adjacent to this ester oxygen right here. However, these 3 proton groups here, which are all identical, have an oxygen separating this ester oxygen here. So what we can conclude is that because the protons on the right are closer to your electronegative atoms, all of these protons are going to be greater downfield shifted than the protons in this molecule because of that spacer carbon group right here. Now, what about for the next pair, so pair B? So in pair B, we actually identified that both these molecules have an internal plane of symmetry. So if I were to determine the number of unique protons, I know that for one type of proton on the left, I'm going to have that same type of proton on the right. So if I take my ratio of blue to green protons, I have a 6 to 4 ratio, which reduces down to 3 to 2. However, for this molecule over here on the right, if I draw all my chemically unique protons, but remember, the internal plane of symmetry goes down through the carbon, so we know that there's going to be 1 proton on either side. So here we have a ratio of 2 to 6, which reduces down to 3 to 1. So the ratio, so the area underneath the peaks of the NMR will differ. So the integration will differ, and we'll have different ratio of integration, so we'll be able to distinguish between these 2 molecules here. So what about this last molecule here? So if we identify that all these molecules actually have an internal plane of symmetry as well. So we can cut this molecule like this, and we can cut the second molecule like that. So I would determine the number of unique proton groups. Remember, what's true on one side of the mirror will be also true on the other side. They'll be the same type. So it turns out I also have 2 types of protons. This is going to exist in a 4 to 6 ratio, which reduces down to 3 to 2. But now what about this molecule here. So if we see this carbon is going through the internal plane of symmetry, so these are all the same types. Remember, what's true on one side is true on the other side. So all 9 of these protons are actually existing in the same chemical environment. And then these 3 protons are also going to exist in this unique chemical environment. So we're going to have a ratio of 3 to 9, which reduces down to 3 to 1. So once again, the ratio, so the area underneath the NMR peaks will differ for these 2 molecules. So you'll be able to distinguish them by their integration values.